Hi guys, so we're going to be starting lesson number 3, images in concave mirrors. All right, concave mirror, that is a curved mirror. In the last lesson, in lesson number 2, we looked at images in a mirror that was flat. All right, we called them plane mirrors, where this is the front of the plane mirror, this is behind the plane mirror, and we looked at objects and their images. And their images were always, if we look at salts, would be the same size. All right, they were upright and laterally or horizontally inverted. Laterally meaning side to side, or horizontal, same side to side. Location was they were the same distance from the mirror as the object, so they were the same. And the type was always virtual. That was plane flat mirrors. Okay, now there are other kinds of mirrors. There are curved mirrors, okay? There's not just flat, plain mirrors. We're going to be looking at one type of curved mirror right now called a concave mirror. And a concave mirror looks like this, all right? It's curved inwards, where this is the front of the mirror and this is behind the mirror, all right? Remember I showed you that when you draw is these little lines that indicate behind a mirror. Okay, so it's a concave. I like to think of it as like a cave. All right, kind of looks like a cave because it's curved inwards. Concave mirrors are mirrors with the reflecting surface curved inwards. All right, let's just pretend this is a volleyball. All right, just because I like volleyball. All right, so the concave surface would be the inside of that surface, the surface that looks like this. All right, so concave mirrors have a reflecting surface with edges that curl towards you, like the inside of a sphere or the inside of an opening of a cave. All right, so here's the inside of a spoon. All that inside is the reflecting surface of a concave mirror. Some makeup mirrors, solar coolers, these are all examples of concave mirrors. Now, concave mirrors are also known as converging mirrors. And there's a reason why they are called that. It's because whenever you have an incident ray going, so these are the incident rays, remember, like that. They're rays because they have, sorry, that one a little off. They have arrowheads on them. They're not straight lines, they're rays with arrowheads. Whenever you have an incident ray hitting the reflecting surface, so this would be behind the reflecting surface, the curved inwards is a concave mirror. That incident ray comes in and reflects in, the reflecting ray comes down into, all right, it converges, all of them. Here's another incident ray coming in, it converges inwards, all right, it goes in. Notice all the reflective rays come in. They go in towards the middle. So they kind of converge onto one point, and this is the focal point, all right? That's why they're also known as converging mirrors. So concave mirrors are also known as converging mirrors because all the reflecting rays bounce off the reflecting surface of the mirror and it will converge to a central point, which is the focal point, all right? They all meet. Converge means to meet. These mirrors can give much different results than a regular plane mirror, all right? However, the laws of reflection still apply, all right? So they still are all found on the same plane, okay? When you look at an object in a curved mirror, the images are distorted. These images get more distorted as you go towards the edge of the mirror, all right? What that means is as a ray, incident ray hits the edge of the mirror, it becomes a little bit distorted. So what that means is it still converges down, but it might, here I'll draw it like this so it's a little bit easier to see. All right, so if an incident ray comes in towards the edge of the mirror, all right, and the edge of the mirror here, they're supposed to reflect back all at the same point. So these ones coming towards the middle, all right, of the mirror, they might reflect straight at the focal point. All right, they reflect back at the focal point. But the incident rays hitting the edge of the mirror, they might just be slightly off. They might not converge right on the focal point. They might converge over here. All right, that's what creates a little bit of a distorted kind of image, and that's called spherical aberration. That's actually called something, spherical aberration. All right, when you have incident rays hitting the edges of the reflecting side of the concave mirror, not converging right at a focal point where all the other incident rays hit, converging maybe slightly to the left or right, away from the focal point, therefore creating a distorted image, a fuzzy image. That's called spherical aberration. Okay, so when you look at an object in curved mirrors, images are distorted. These images get more distorted towards the edge of the mirrors, called spherical aberration. So let's take a look at the diagram for curved mirrors. There's a couple of things you need to know. So first thing is the principal axis. It's a straight line passing through the midpoint of the mirror. So here is the principal axis. It's a straight line. I'm trying to follow it as fast as I can, going right through the middle point of the converging mirror. So here's the back of the mirror, all right? This is the front of the mirror. This is the behind the mirror. So this is behind, this is in front, okay? So this right here is known as the principal axis. This line here goes right, intersects right in the middle of the curved concave mirror. The center of curvature, all right, is the center of the sphere of a mirror it fits on. So if I were to draw a mirror here, a concave mirror, right, and if I were to go my principal axis right through it, if I were, let's just say, to extend that mirror to this side, that creates a circle, right? And the middle of that circle would be the center of curvature, all right? That's the center of the sphere of a mirror that fits on. So that would be the center of curvature. So here is the center of curvature, okay? But we don't have that. We just have the one. This is what we have here. This is what we see, okay? The focal point is a point at which light rays parallel to the principal axis converge when reflected off of the concave mirror. So it's exactly halfway between the center of curvature and the vertex. So I think I missed that. So what I mean is, let's go back to the vertex. So the vertex is the point right here. It's the point where the principal axis meets that middle of the mirror, the center of the concave mirror. That's the vertex. The center of curvature I talked about. Now the midway point between the center of curvature and the vertex is the focal point. And going back up here, remember how I said all the incident rays, except when they go towards the edges, they converge onto a point, and that point was called the focal point, all right? That is halfway to the center of curvature, all right? So that would be the half of the center of curvature. So if my center of curvature, let's say, is 30 centimeters from my concave mirror, well, then my focal point would be half of that, would be 15 centimeters, okay? So focal point, a point at which light rays parallel to the principal axis converge when reflected off a concave mirror, is exactly halfway between the center of curvature and the vertex. The focal length, so here's our focal point right here. The focal length, which is indicated by a small f, focal point is indicated by a large F, uppercase F. The focal length is the distance between the vertex and the focal point. Okay, so from the mirror to the focal point is the focal length. Okay, ray diagrams for concave mirrors. So, ray diagrams for curved mirrors are different than ray diagrams for planar mirrors. There's no measuring of distances or angles between these ray diagrams. So remember I told you, here's a plane mirror, here's your, let's say, line. I want to draw the image of that line. I just have to measure from here to here, measure that length, and then I measure the equal distance from here to here, and I draw my line. Do another measurement with a ruler, here to here, draw another measurement here to here, and then I find my image for that line. For a curved mirror, there's no measuring, all right? There are 3 rules that you have to follow in order to create ray diagrams for concave mirrors. Okay. Normally I have color kind of pencil crayons to draw this in the classroom, but I'm just going to have to do my best here, okay guys? There are 3 rules that must be followed in order for this to happen. Rule number 1, any incident ray that travels parallel to the principal axis reflects back through the focal point. So here's my object. All right, let's go through some stuff again. This is my concave mirror. All right, that is in front of the mirror. This is behind the mirror. Remember, it shows, these lines show behind the mirror. This is my object, okay? This object is further, its position is further than the center of curvature. So it's beyond the center of curvature is what that means. The first rule, when I draw my incident ray, it goes from the top of the object striking the reflecting concave surface. Now it's a ray, so it needs to have an arrow. That's an incident ray. I need to draw my reflective ray. How does that reflect? Well, it reflects back straight through the focal point. Remember, this is a converging mirror, so it's going to reflect straight back through the focal point. It needs an arrowhead because it's a ray. So draw an incident ray from the top of the object straight through to the focal point. Sorry. Draw an incident ray from the top of the object parallel. This means it's parallel, right? Parallel, okay, to the principal axis, hitting the mirror. And then that reflects back straight through the focal point. You would be using a ruler, okay, guys? So that is my first rule. Let's take a look at the next. Let's draw my second one. So first one is, remember, guys, okay, straight through parallel to the principal axis, hitting the reflecting surface. Then it reflects back through the focal point right here, okay? Now, when you're drawing these, incident rays do not go behind the mirror. Reflective rays can go behind the mirror. That's very key, all right? So if I wanted to extend this back behind the mirror, I could. I cannot do that for my incident ray. The first ray I drew, I cannot do that. All right. Now, my second one is, I go from the top of the object down through the focal point. It's a ray, so I need an arrowhead hitting the reflecting surface, all right? Let me say that again. Top of the object, straight down through the focal point, hitting the reflecting mirror. How that reflects back is it reflects back parallel to the principal axis, okay? Once again, reflective rays can go behind the mirror. And I show that by showing a dotted line. Only when you go behind the mirror, the lines have to be dotted because they're not real, they're fake, all right? There you go. So let's draw. You can do a third rule. You don't have to do the third rule, but I'll show you just for fun, all right? Here I've got, so this should be extended a bit. That would be the extended part of my mirror, all right? So let's just extend that a bit. Okay, so the third rule I can do is any incident ray that goes from the top of the object straight through the center of curvature, hits the reflecting surface, bounces back on itself. So it's going to bounce back on itself like that, all right? Now, the reflective ray can go back because remember, the reflective ray is going back in the same path that it took as the incident ray, so that can go back. All right. So that's what that says. Any incident ray that travels through the center of curvature will reflect back on itself, okay? Now, so let's take a look. The first rays are in blue, okay? Once again, first incident ray, top of the object, striking the reflecting surface parallel to the principal axis. That reflects back through the focal point, okay? You can also go back here like this, reflective ray. The second one was in green, top of the object, through the focal point, reflects back parallel to the principal axis. All right, and the third one, you don't have to do the third one. It's just there in case you need it. Top of the object, through the center of curvature. All right, back through the onto the center of curvature. Now, reflective rays can go backwards. Remember, first incident. This is an incident ray. This is an incident ray, and the first one is an incident ray. This is a reflective ray. This is a reflective ray. Reflective rays can go back behind the mirror, all right? So this was my reflective ray. It can go back behind the mirror. Now, this is the key, all right? The point where 3 or 2, if you don't want to do the third case, if you don't want to do this red line, Two reflective rays cross, they intersect, they meet. That is the point, the top of the image. So my object was the pencil. The top of that object meets where the two reflective or three reflective rays meet. So let's take a look. This was one reflective ray. This was another reflective ray. All right? It meets right here. So this is my pencil right here. All right? So that is the top of the pencil. That is my image. So this is the image of the pencil. Okay? So this is what we're going to look back here. Remember I told you you only need two incident and reflective rays? What you got to see is, where do the reflective rays meet? All right? Where do the reflective rays meet? The first reflective ray was this one. And then the second reflective ray we drew was this one. So where do they meet? Well, they intersect right here. So this is the top. Now, whenever you're drawing an image, it's got to be from the principal axis down. So this is my pencil right here. And this is the top of the pencil. All right? So really, it's upside down. And that's important because you need to do your salt characteristics for this image that we just did. All right? So let's take a look. Okay, so we did, the first case was an object that was beyond C, right? It's further than C to the image, to the reflecting surface. So the size, let's take a look at the size. Well, it's smaller, right? This looks smaller than the object. So it's smaller, it's inverted, it's upside down, all right, is its attitude. The location, it's in front of the mirror between C and F. So it's right here, it's in front of the mirror between C and F. Or you could say it's closer to the mirror. It's in front of the mirror between F and C, and it's real. How do I know it's real? Because it's in front of the mirror. Okay, guys? Now, that was just one scenario. That's when the object is beyond C. Okay? There are others. So this is what I'm going to draw for you. Okay? So let's do it again. Okay? Object is beyond C. This time the object is an arrow. I like to do arrowheads. So top of the object is my first incident ray, parallel to the principal axis, striking the reflecting surface. Let's just draw my lines to show that this is behind the mirror. Okay? Now, how is that incident ray going to reflect back? It's going to go from the point where you hit the reflecting surface. It's going to reflect back straight through the focal point. You need an arrowhead. Now, reflective rays can go behind the mirror, so it's going to extend back as a dotted line. That was my first incident and reflective ray. The second one, top of the object, straight through the focal point, hitting the reflecting surface. Needs an arrowhead. How does that reflect back? So this was my first incident ray. This is my second incident ray. This was my first reflective ray. Now, how does this incident ray reflect back? It reflects back straight back through, okay, straight back. Sorry, that's not straight. Normally I would be using a ruler, but it's hard to do that with the computer screen. Straight back, okay, parallel to the principal axis. This is a reflecting ray, so it can go back, dotted line behind the mirror. All right, look at that. We've already got two reflective rays that meet, that cross, okay? So where do they cross? They cross right here. So what I'm going to do is draw my image. So this was my object. Now I'm going to draw my image. My image always starts at the principal axis and it goes down, all right, to here. And that's where it meets. So it'll be upside down, okay? I don't do this. If this is where my reflective rays meet like this, and this is my principal axis, I don't do this, okay? That would be wrong. It's not like that. It goes from the principal axis down and the arrow is the tip. All right? So there you go. That is my image. So let's take characteristics of the image. Okay? The size is smaller. Attitude is inverted. It's upside down. Location is between C and F. And the type is real because it's in front of the mirror. Let's do another case. All right? The other case is object at C. So the object is at C right here. All right, let's do our rules. First incident ray, top of the object, straight through parallel principal axis, hits the reflecting surface. Okay, that reflects back through the focal point. All right, that's a reflective ray, so it can go behind the mirror. We're going to draw that dotted. Okay, that's my first incident. That's my first reflective ray. Now, next incident ray, top of the object. Oops, sorry guys, that was off. Top of the object. Okay, top of the object, straight through the focal point. Needs an arrowhead. Okay? Then, how does this, so that's my next incident ray. How does that reflect back? Reflects back, straight back. Okay? Arrowhead. Reflects straight back, parallel to the principal axis. I'm not going, this one is a reflective ray, so it'll go back as well. I'm not going to draw another, you can't even do this in the next one where it goes through the center of curvature because it's on the center of curvature. The object is on the center of curvature. So how are my characteristics of my image? Well, let's see. Do I have two reflective rays that meet? That was my first incident ray. That's my second reflective ray. There's my next incident ray. There's my next reflective ray. Right here, that's where they meet. It's not straight, so we might be a little bit off in the normal characteristics. Once again, I draw my image from the principal axis down to where the two reflective rays meet. Okay? Now, let's take a look over here. Because at C is supposed to be, it's supposed to be at C, but because my lines aren't straight, and you might not get this, it's very hard for it to get at C. So we'll just say it's at C, but really it's just a little bit in front of C. So same size, attitude is inverted, location at C, even though I know it's not at C, but my lines aren't very straight, and this is in front of the mirror. So what is this? Is it real or virtual? It is real because it's in front of the mirror. Okay, so that's case number 2. All right, at C. Same size, inverted, in front of the mirror, at C, and it's real. Let's take a look at the next case. All right, concave mirrors, they have 5 cases. So I'm going to go through all 5 with you. All right, so this time the object is between C and F. Okay, so there's my object. Let's take a look. Let's go through the rules. First incident ray. Top of the object, straight through, parallel to the principal axis. This is the principal axis, the blue dotted line, to the reflecting surface. How's that going to reflect back? It's going to reflect back straight through to the focal point. All right, this is a reflecting, so this is my incident. This is reflecting, so what do reflective rays do? They can go back behind the mirror as the dotted line. Okay, next incident ray. Top of the object, through the focal point. All right, that's my next incident ray. Okay, how is that going to reflect back? It's going to reflect back, straight back. So there's my thing. Sorry guys, this isn't very straight, but I'm trying my best. Straight back. All right, parallel to the principal axis. This is a reflecting ray, so it can go behind. All right. At some point, this is my other reflected ray. At some point, I'm going to have 2 reflective rays meet, intersect, and they do. They do so right here. So there's my image, okay? Let's see what it says up here. So between C and F, it's larger, it's inverted, it's in front of the mirror beyond C, and real. Let's see if I did that correctly. Okay, where am I here? There we go. There's my image right here. All right, it's definitely larger. It's inverted. Location is beyond C. Good. And it is in front of the mirror, so therefore it is real. Excellent. Okay, that's the first case. Let's look at the next case. The fourth one is object is at F. All right, so it's on top of F. Let's see. It says here no image is formed. I wonder why. Well, let's take a look. All right, top of the object, straight onto the mirror. Okay, that's my first instant ray. This is behind the mirror. Then straight, and then it reflects back straight through the focal point. Okay, there's my reflected ray. Top of the object through the focal point, I can't do it because it's sitting on top of the focal point. This is where the third ray comes in. Center of curvature. Okay, now this is interesting because normally we would go top of the object through the center of curvature, but the center of curvature is behind the object. So in this case, I would go center of curvature, top of the object, right? And then how does that reflect back? It reflects back on itself. So it's going to go backwards on itself, and it's going to go behind the mirror because it's a reflective ray as well. Now, look at nothing. There's no reflective rays intersecting. These two do not intersect, right? This reflective ray and this reflective ray don't intersect, and behind the mirror they don't intersect either. So therefore, no image is formed because we know an image only is formed when you have two reflective rays meeting, intersecting. So this would be no image. Okay? And this is the only case when the object is sitting on top of the focal point that there'll be no image. Let's take a look at the last one. This one is an object between F and the vertex. So between the focal point and the vertex. So let's just do that here. Let's do our rules. First instant ray, top of the object through to the reflecting surface, parallel to the principal axis. Need an arrowhead, all right? Then it reflects back through the focal point. This is my reflective ray, so it can go back behind the mirror, all right? Now, how else does it come? How else does the second rule? Now, remember, this object is in front of the focal point. So we're going to go from the focal point to the top of the object. Normally, the object is here, and we go from the top of the object through the focal point. But this time, the object is in front of the focal point. So we're going to go from the focal point to the top of the object. Oops. Focal point to the top of the object. That's my incident ray. And how does that reflect back? Same as before. Back parallel to the principal axis. Now this is a reflecting ray. So the reflecting ray can go back as a dotted line. Remember, reflecting rays can go back behind the mirror, not incident rays. Now, I already see a place where the two reflective rays cross. They cross right here in behind. So now my object from the principal axis up to the point where the reflective rays meet, that's where my tip of my arrow is going to be right there. That is my image right here. All right? So, what are the characteristics of that image? Size, larger. Attitude, it's upright. Okay? Location is behind the mirror. All right? And therefore, if it's behind the mirror, it is virtual. So let's take a look at what the characteristics stay up here just so that we're consistent. So once again, at F, no image is formed. The last case was between F and the vertex. Is larger, upright, behind mirror, same distance as object, okay? And virtual, okay? So that's the last one we just did, which was right here, okay? It's the same distance, roughly, okay? And if my lines were a little bit straighter, they would be the same distance, but it's definitely larger, it's definitely upright, it's definitely virtual, okay? So those are the 5 cases. Now, you can just memorize those characteristics of each case, right? You can memorize that the object, if an object is between F and V, these are always going to be the case for that. You can memorize it because it's actually quite easy because this is the only time when the object is going to be in a concave mirror, upright, and virtual, okay? You can memorize that when an object is at F, no image is formed. You can memorize when an object is between C and F, these are always going to be the characteristics. You can just memorize that. When the object is at C, these are always going to be the characteristics. When the object is beyond C, these are always going to be the characteristics for it. So you don't have to draw the ray diagrams. They're just there to help you. I like drawing the ray diagrams, but you can, if you don't know how to do them or you don't understand how to do the ray diagrams, you just memorize these characteristics because they're always going to be the same for each of these 5 cases. So really, all you have to do is memorize this chart if you want to. I can't quiz you on the ray diagrams because we're not, like, I'm not with you. You can do these sheets, these practice questions down here though. Okay, there's definitely practice questions you can work on to practice your ray diagrams. The purpose of the ray diagrams is to help you get these characteristics of the image. Let's take one last look at applications, all right, of concave mirrors. So where do we see concave mirrors in real life? A concave mirror in the shape of a parabola that can send and receive radio waves is a radar antenna, all right? A radio wave generator, detector, or located at the focal point. A pulse of radio waves hits the antenna and is sent towards the sky. Any returning radio waves that reach the antenna are directed towards the detector at the focal point. Another application of a concave mirror is a solar oven. It's a concave mirror that collects and focuses the sun's energy, allowing people to cook food without the use of fossil fuels, say for example, wood or propane. Any reflected rays converge, remember another way of saying concave mirror is a converging mirror, at the focal point, and concentrated rays of light at the focal point are converted to heat. Here are some practice questions that you can answer about concave converging mirrors. You can answer those, they're beneficial to you. And then here is a concave mirror diagram worksheet to help you come up with the SALT characteristics for each of the image. So here would be an object that is beyond C, what are the characteristics? An object that is between the focal point and the vertex, an object that is at C, an object that is at the focal point, remember that's the special one, and then, this one is upside down, this one already, so what would it be? That's a tricky one, try to do that one. And then here's another one, object beyond C, but it's inverted, all right? This is an object that's between C and F. We did that one, he looked like this instead. But you guys try it this way, okay, guys? So you can do that. And then I'm going to make another video for the convex mirrors, the second type of curved mirror.